Hi, my name is Florent Mathieu. We're going to do a video today about demoing the two main EikoTwin DIC workflows for measuring stress, strain, and displacement maps. I'm just going to focus on measurement, not so much FEA comparison, but just these phases that explain how you can measure strain maps and displacement maps from images. So we're going to start with just maybe the most direct route, which is also actually the most recent. And to showcase this, I'm going to open a few images, which are actually a set of synthetic images that we generated with EikoTwin Virtual, which is, as you see, a simple tensile test. This is just synthetic images, so it does not anything around it. We're going to straight away load calibration images. Our calibration images are actually Charuko target images that looks like this. Just to show you what a Charuko target looks like. This is synthetic as well, obviously. The Charuko means chessboard Haruko, and Haruko is a library of these markers that you see here that are to be detected by the system. So in this case, we have, I think it's 15 by 22. So we're just going to create this here, this library. This is 4 millimeters, 3 millimeters, and 5 bits. They're synchronized because they have been generated for the same camera pauses. So we're just going to import, was it camera 1? Yes, camera 1 calibration images. We started the intrinsic parameter computation, which is just what you can do when you have one set of calibration images, but then we're going to select the same for camera 2, which is also giving the software the ability to calculate intrinsic parameters that are linked to the camera itself, but also the stereo calibration, which is the correspondence between the locations, orientations of the cameras with respect to another. This has been nicely done, it seems, which makes us able to continue to the selection of the region of interest. This is something that we here for this workflow we're going to do from the image, because this is actually the simplest way to do it. So we're just going to here draw kind of a polygon shape, mask, however you want to call it, onto the image. And this is it basically for image 1. Oh, this was camera 2, sorry. So let's do it also for image 1. And this is actually from the mask from image 1 that we're going to draw to generate the mesh just right after. Here it is. This is, well, depending on your shape, but this can be pretty straightforward. Okay, so we have our eye, we can go to mesh, and then we're not going to select a file from which to import the mesh. We're just going to do from the region of interest and mesh this zone. Let's take 100 pixels for the sake of computational time. This is a pretty coarse mesh, obviously. This is generated directly from the left image or camera 1. And from that, we can go to reconstruction. And for reconstruction, you just have to click this button and calculates the correspondence between left and right image with the AC actually, and reconstruct the 3D shape based on the calibration. So you see here that as we expected, we have a pretty flat surface, which is to be expected in this case. And you can see how the mesh reprojects onto the image. This is a pretty coarse mesh in this case, but the speckle pattern is too, so it's actually pretty fitting. Okay, we can go now to the displacement tab. which is just basically setting the right parameters and just running the computation. So here we can we can put a little bit of filtering. Yeah, the average size is 3 millimeters. Let's put 10 for instance. Brightness and contrast correction is always nice. Displacement, even if you don't really need it here because these are synthetic images. Initialization helps with larger rigid body movements. And let's just run the measurement itself. So here you see that the software runs initialization and then runs the iterations for the DIC algorithm itself. And as soon as we have results, we can actually display, let's for instance, displacement fields. Here X is actually the main direction, and here it is for each image that the software is processing. It then directly displays the displacement field that has been measured. Okay, this is actually for the most part done now. We have measured the field. I will show at the end of the video how to add sensors to it in a simple way. But now I'm going to focus on the other workflow, which is selecting a region of interest from a mesh, an existing mesh, and measuring the displacement field directly on this existing mesh file. So for that, we are going to go to this tab again, going back to From Mesh, and then on the mesh, in the Mesh tab, we are going to load an existing mesh, which is going to be here the input file, Abaqus input file for this particular specimen, which is pretty coarse as well. We can select the region of interest in two ways. We can either create a zone like this, which is maybe not the most convenient here. We can cancel this. I actually like to pick angle in the case that we have everything visible from face, because when you add a zone, yes, you click an element, you add everything that aligned with this with this element, and we just validate. And here we are. We can now go to pre-calibration, which is alignment of mesh and image, and this alignment is done manually. So we have to select points that we see are both in the mesh and the image. So here, these are natural fiducials that you can select. This is pretty simple in this case, obviously. And we are just going to do the same for the left and right images. So here with my little focus tool, it's a little bit easier. I'm just roughly selecting the corners. If you don't have corners on your specimen, or if you have a pretty simple geometry, you can also draw marks or grids on it. Here, I just don't want to click the points again, so I can copy the points from camera 1 on the 3D parts, and I'm back at it on the image side. And these points will allow to make a correspondence as well between left and right image, which is going to help also reprojecting the mesh onto the surface. You can see here that these have been pretty well projected. And we can then go to the calibration itself. Calibration for intrinsic and extrinsic has been done, so we just have the shape measurement to do here. Just going to take the same regularization length as before and just run the calibration. Okay, this is just the shape, which is a little bit tilted from the original position, which is okay. And then we go to displacement, and just like before, we are just setting up the same parameters which are still here, and here you see the displacement field showing up, just like what we had previously. The main difference is obviously that now we did the measurement on one surface of an existing mesh rather than generating a mesh. The main advantage to do that is obviously to be able to compare with the simulation result, which can be done here. I don't have a simulation for this file, so we don't need to do it now, but obviously this is the main thing about EikoTwin DIC that I will be showing an example right at the end of the video. Just wanted to show you before that the sensors tab, how to create a sensor. This is pretty straightforward. For instance, a displacement sensor here. If I want this node to have a sensor on it, I can then create a chart. Let's call it displacement, and I can select X, Y, Z coordinates for it to draw the displacement that have been measured here. I can do the same for a strain gauge, for instance. Let's do it, for instance. Oh, sorry for that. Okay, let's just click allocation. Oh, here it's pretty big, so I can do a 5x5, for instance, strain gauge here. You see it's right size now. Let's create another graph for strain. And here I can just draw, different components of my strain gauge that are directly computed from the DIC field that is present here. We have a bunch of other sensors that you can, well, everything's in the manual, but we can draw extensometers, profiles, and even for users of the thermal plugin, thermocouples and pyrometers. Okay, so now I'm going to show you another example with the FEA DIC comparison. Okay, so this is a case that I loaded up that showcases um, a case where we actually have a mesh, as you can see here. And if I zoom in, let's say put myself at the last image, displacement Y, this can show you how you can superimpose the simulation and DIC result. You cannot see that very clearly here. This is the zone that we use for measurement. I can show it here as well. Okay, this is the zone of the wing here that we selected, and we have a displacement field, but we also have a displacement field that comes from the simulation. That is here, if I remove the DIC result, this is the simulation result that we loaded from the ODB file in this case. And we have also the DIC result, which means that the software automatically computes the difference between those two fields on the region of interest, and this is the difference between those two. Another way of looking at it is amplifying the displacements, such as like this, for instance. And here you see that if you amplify, I'm sorry, I'm going to put myself in a better angle. If you amplify the displacement here, you can see that the measurements seems to be deforming more than the profile of the wing here, which shows you a difference. And this is the kind of animation that you can do, but also obviously put a sensor on the mesh itself. No, that's good. There's already one here. So if I go to the sensors here, and if I select here, you see now that we have the simulation component, but also measurement component, just like we had before. And you can see that those two are different in this case. Yes, okay, here it is. Thank you for watching the demo. Feel free to come to us with any question, whether it is in the comments or via email. There's contact link in the description, and yeah, have fun with the DIC. Bye bye.